All right, let's dive right in. Today, we're going to crack open the toolbox that engineers use to control and really to master one of the most powerful forces in the universe: energy. I mean, have you ever really thought about that? We're talking about these massive, almost unimaginable amounts of energy. So, how do you possibly keep track of all of it without things, going boom? It's a huge, huge challenge, but engineers have a very specific, very systematic way of handling it. And that's really the secret right there. It's not guesswork, it's not just intuition, it's a precise set of tools and rules. So, for the next few minutes, we're going to explore that exact toolkit and see how they account for every single bit of energy in any given system. Okay, so first things first, every great toolkit, I don't care what it's for, needs a solid foundation, a fundamental principle that everything else is built on. Well, for energy, that foundation is one absolutely unbreakable law. This right here is the first law of thermodynamics, the law of energy conservation. And honestly, the best way to think about it is like a bank account. You can't just create money out of thin air, and money doesn't just vanish into nothing. Every single dollar has to be accounted for, right? Whether it's coming in, going out, or just sitting in your account. For an engineer, it's the same deal, but for every single joule of energy. So if energy is like the money in that bank account, how do engineers actually, keep the books? Well, they use a kind of energy ledger with two main columns, and which one they use depends entirely on the system they're looking at. These are called internal energy, which we label with a U, and enthalpy, which gets an H. Let's start with internal energy, or U. This is the go-to tool for a closed system. So imagine you've got a sealed, totally rigid box. The total energy of all the molecules just rattling around inside, all their kinetic and potential energy combined, that's the internal energy. The key is nothing is flowing in or out. But what about an open system? Like a pipe with water constantly flowing through it? For that, we need something different. We need enthalpy, or H. Now, enthalpy includes all that internal energy we just talked about, but it also includes the energy needed to actually push that fluid into the system and shove other fluid out of the way. It's the total energy of a system that's in motion. So, here's the bottom line. It is absolutely crucial to pick the right tool for the job. If you're looking at a sealed tank, you use internal energy, U. But if you're analyzing a turbine or a pump or a chemical reactor where stuff is constantly flowing through, you have to use enthalpy, H. Using the wrong one would be like trying to balance your personal checkbook using a giant corporation's accounting software. The numbers just wouldn't make any sense. Okay, so we know we need to find the value of H, of enthalpy. But how? I mean, do engineers have to calculate this from scratch every single time? Well, thankfully, no. The very first tool they reach for is the reference manual. For super common and really important stuff, especially water, engineers have these amazing resources called steam tables. They are these incredibly detailed charts that literally just tell you the exact enthalpy for water at pretty much any temperature and pressure you can think of. It's a massive shortcut. It's the ultimate cheat sheet, and it saves a ridiculous amount of time. But that kind of raises an obvious question, doesn't it? Steam tables are fantastic for water. But what if you're working with some complex chemical that isn't in a nice, neat table? You can't just throw your hands up and give up. And this is where the real clever engineering problem-solving kicks in. And here's the trick. It's really brilliant. Because enthalpy is what we call a state function, which just means it only cares about the start and end points, not the journey it took to get there. Engineers can invent a simple, totally imaginary path to calculate it. They break a really complex change down into a series of super easy steps. A little change in pressure, then a change in temperature, maybe a phase change, and so on. They calculate the energy for each simple step and then just add them all up. It's so clever. Now, of all those little steps on that imaginary path, by far the most common one is figuring out the energy needed to change a substance's temperature. And for that, there's a specific, absolutely crucial tool. That tool is called heat capacity, or CP. And I love this analogy. Just think of it as the price of heat. It tells you exactly how many joules of energy you have to pay to raise the temperature of 1 mole of something by 1 single degree Celsius. Some materials are cheap to heat up. They don't cost much energy. Others are very, very expensive. Now, this table might look a little intimidating at first, but it's really just that price list we were talking about. You want to heat up acetone? Okay, here are the coefficients for its price formula. Air, right here. Calcium carbonate? You got it. Engineers use this table to find the exact price to heat hundreds of different compounds. All right, you probably know what's coming next, right? What if your specific compound isn't on this list either? Let's say you're designing a new process using a totally new material. What do you do now? Do you have to run years of experiments just to figure it out? Nope. The toolkit has one more clever trick up its sleeve. It's called Kopp's rule, and it is such a powerful little shortcut. The idea is wonderfully simple. If you don't know the heat capacity of a whole molecule, just estimate it. And you do that by adding up the heat capacities of all the individual atoms that make it up. It's an approximation, for sure, but it's often a surprisingly good one. Let's see exactly how it works. First, you go to a different price list, but this one isn't for molecules, it's for individual atoms. So this table gives you a pretty good approximate heat capacity value for a carbon atom, a hydrogen atom, an oxygen atom, and so on. And step 2? It's just simple addition. That's it. For calcium hydroxide, for instance, you take the value for one calcium atom plus 2 oxygen atoms plus 2 hydrogen atoms. You add them up, and you get an estimate of 79. Now, the actual measured value is 89.5. I mean, for a quick back-of-the-envelope calculation, that is ridiculously close. It's an amazing tool to have. Okay, so we've looked at a bunch of individual tools. Let's zoom out for a second and put the whole toolkit together. Let's see the big picture. So here it is, the whole process. You always start with the golden rule. Energy in equals energy out. You use your ledger, enthalpy, to track the energy in any flowing system. You first check your reference manual, the steam tables, to see if there's an easy answer. And if there isn't, you pull out your calculator, that hypothetical path using heat capacity, to figure it out. It's a complete logical system. And this right here is why it all matters so much. This toolkit is the difference between hoping a chemical plant is safe and knowing that it is. It's how we design everything from our power grids to life-saving medicines with incredible precision and control. It's about taking the unbelievable power of energy and making it work for us, safely and reliably. So think about that. Behind every single great feat of modern engineering, every bridge, every power plant, every single thing, there's this invisible framework of calculations, a toolkit, just like this one, making sure that every single joule of energy is exactly where it's supposed to be.